8 studies published on the same day in March 2025 challenged two of the biggest ideas in modern physics. They suggest that dark energy, which we thought was responsible for the expansion of our universe, might not be the cause after all. Even more surprisingly, they raise the possibility that entropy might not always increase. The studies show that the strength of dark energy has changed over time. This is such a major discovery that we may need to rewrite both the theory of the expanding universe and the second law of thermodynamics. If dark energy changes across cosmic eras, it could reshape almost all of physics. According to the second law of thermodynamics, entropy or disorder in the universe must increase. Almost every law in physics depends on this idea. But hold on. If dark energy is not constant, and even more strangely, if it is decreasing, what would happen to entropy, the foundation of all physical law? Einstein once added a cosmological constant to his equations of general relativity to support the idea of a static universe. But when Hubble discovered that the universe was expanding, Einstein called it his greatest mistake. Ironically, in 1998, when dark energy was discovered, Einstein's constant was brought back to explain the accelerating expansion of the universe. Now DESI, the most advanced dark energy telescope in the world, is suggesting that even this revived constant from 1998 might not be constant at all. How is that possible? Data from the Dark Energy Spectroscopic Instrument, or DESI, points to dark energy evolving over time. If this is true, cosmology will need a new model. But why? The current lambda-CDM model, which stands for lambda cold dark matter, treats dark energy as a constant force in the universe. But while everything else in the universe changes, assuming that dark energy stays constant, especially when we still don't even know what it really is, might no longer be accurate in light of DESI's latest results. Although the published papers have not yet passed peer review, 8 independent studies reached the same conclusion on the same day. Even more importantly, they confirmed and expanded on earlier analyses from 2024. In short, the current cosmological model is now being questioned. Although often overlooked by the classical physics community, the issue of Hubble tension has resurfaced in the scientific world, especially after the first data from the James Webb Space Telescope. The Hubble constant is a value that defines the rate of expansion of the universe and is considered one of the cornerstones of modern cosmology. However, in recent years, the two main methods used to measure this constant have produced inconsistent results. This has created a serious contradiction in calculations of the universe's expansion rate and age. Based on current data, it is now almost certain that the Hubble constant is not truly constant. Yet interestingly, this issue was not studied in depth for many years and did not take center stage in major research. That changed when DESI presented new data that could completely shake our understanding of the Hubble constant and the current cosmological model. According to the standard model of cosmology, the Big Bang occurred around 13.8 billion years ago, beginning from a point of infinite density. In its earliest moments, the universe was an extremely hot and dense plasma. Over time, it cooled down, allowing atoms, stars, and galaxies to form. But the expansion did not stop there. Observations have shown that the universe is expanding at an accelerating rate. The cause of this acceleration is believed to be a mysterious force called dark energy, which is thought to make up about 70% of the universe. Dark matter, on the other hand, makes up about 25% and provides the invisible gravitational glue that holds galaxies together. The remaining 5% consists of ordinary matter and light. In the current model, dark energy pushes the universe to expand faster, while dark matter and normal matter try to slow it down. Because dark energy is dominant, scientists believe the universe would continue expanding forever. But recent studies suggest that dark energy might not actually be constant and could change over time. If this is true, we will have to rethink everything we know about the expansion of the universe. The current cosmological model might not be able to fully explain how the universe expands. First, let's look at how this research was carried out. It all started with a need to question the current model of cosmology. Then came a need for an advanced telescope system capable of directly measuring dark energy. That's where DESI comes in. DESI stands for the Dark Energy Spectroscopic Instrument. DESI is a high-tech telescope system developed to understand the expansion rate of a universe and the nature of dark energy. It was designed under the leadership of the United States Department of Energy's Fermi National Accelerator Laboratory, with contributions from more than 25 institutions and over 400 scientists. Construction began in 2015, and the system became operational in 2020. It is installed on the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona. One of its key components is the 570-megapixel dark energy camera, known as DCAM, and a set of 5,000 fiber optic spectrographs. This system was designed using cutting-edge technology from start to finish and was developed under U.S. coordination with the support of countries focused on producing science. What makes the dark energy camera different from others is its extremely wide field of view and its 62 special CCD sensors, which can measure redshift with incredible precision. Thanks to these features, DESI can carry out the most detailed observations ever made about dark energy. The system also includes 5,000 fiber optic positioners, allowing it to collect spectroscopic data from 5,000 different galaxies at the same time. This advanced optical system speeds up observations and allows scientists to gather the most comprehensive data on the expansion of the universe and how dark energy changes over time. How does the DESI telescope system measure dark energy? Something we still don't fully understand. Scientists studied 15 million galaxies over a period of 3 years to reach this conclusion. To grasp the scale of these measurements, it's enough to look at the universe map created from the data. On this map, the structure of the Milky Way galaxy and the surrounding stars can be seen in remarkable detail. This discovery forces us to rethink our entire theory of cosmology. To simplify how the system works, let's take a closer look. Type I supernovae provide critical data for understanding the expansion rate of the universe and the level of dark energy believed to drive this expansion. If the universe were expanding at a constant rate, or if dark energy had stayed the same, the redshift of these supernovae would follow a predictable pattern. But DESI's observations revealed that supernovae exploding at different times show different redshift behavior. This means the expansion rate of a universe or the level of dark energy may have changed over time. Scientists did not rely only on redshift measurements. To confirm their findings, they also used baryon acoustic oscillations, or BAOs. So what exactly are BAOs? In the early universe, matter was mostly in the form of plasma and it experienced density waves. These waves spread like sound and left visible patterns in the distribution of galaxies that we can still detect today. But BAOs are more than just sound waves. They are frozen relics of photon-baryon plasma from the early universe. Around 380,000 years after the Big Bang, when the plasma cooled and atoms formed, these waves suddenly froze in place. By studying BAOs, DESI can compare the expansion rate of a universe 11 billion years ago with the rate we see today. It works almost like a cosmic time machine. Normally, if dark energy had remained constant or if the expansion rate of the universe had never changed, these sound waves would have left behind imprints roughly 500 million light-years across. But the measurements show that this distance has changed over time. These results, combined with redshift data, strongly suggest that dark energy has evolved throughout the history of the universe. His study is based on observations of 13.1 million galaxies, 1.6 million quasars, and 4 million stars. The focus of the research is on baryon acoustic oscillations and redshift distortions. To process such a large data set, the information was transferred to the National Energy Research Scientific Computing Center. For redshift analysis, scientists use software called RedRock. This program uses artificial neural networks and advanced artificial intelligence techniques to extract redshift measurements quickly and accurately from massive data sets. For the analysis of baryon acoustic oscillations, they used a tool called Python code for IGM cosmological correlations analyses. Research like this is only possible with not just advanced telescopes, but also cutting-edge data processing and analysis systems. The universe map created from DESI's first data release is considered one of the most detailed maps ever made. It shows galaxies and quasars up to a redshift level of about z equals 4, centered around Earth. The map spans a diameter of about 45.6 billion light-years, covering at least half the observable universe by size and about 10% by volume. Using these maps, scientists compared the redshift levels of galaxies with the predictions of the standard cosmology model and found striking results. So what were these results? According to DESI's data, baryon acoustic oscillations were measured to be 4% smaller than predicted. This is a major result that contradicts the standard lambda-CDM model's assumptions about the expansion rate of the universe. A 4% smaller scale means the universe is expanding more slowly than the standard model predicts. According to the model, the expansion rate should be constant. But these new findings suggest that dark energy, the force thought to drive expansion, may have decreased over time. Similarly, the redshift measurements show unexpected differences in the universe's expansion rate. DESI analyzed the redshift of 18.7 million celestial objects, creating the largest extragalactic redshift dataset ever recorded. The results show that objects are showing about 0.38% less redshift compared to what would be expected in a constant expansion. The biggest deviation was observed in quasars, with redshift about 1.8% lower than expected. These results clearly show that the universe's expansion rate is not constant and that at certain points it expanded more slowly than we expected. If confirmed, this supports the idea that dark energy does not accelerate expansion at a steady rate, but may change over time. This could be powerful evidence that the current cosmological model needs a major revision. So what happens now? First, we need more precise and more frequent observations. But DESI is not alone. The European Space Agency's Euclid telescope was launched in 2023 and will map 10 billion galaxies over 6 years. When DESI and Euclid data are combined, scientists believe the mystery of dark energy could be solved with 99.9% certainty. Cosmology is no longer a blind debate. It is becoming a global race among nations focused on producing real science. The idea that dark energy and the expansion rate of the universe may not be constant forces us to rethink the Big Bang-based cosmology model. If dark energy truly changes over time, this could mean the expansion of the universe might slow down or even reverse. This could bring back 3 major cosmic scenarios for discussion. The Big Crunch. If expansion slows down enough and matter becomes gravitationally dominant, the universe could collapse back into itself. The Big Bounce. The universe could exist in cycles of expansion and contraction, bouncing between each phase endlessly. The Big Rip. If dark energy increases during certain periods, expansion could speed up so much that galaxies, stars, and even atoms are torn apart, ending the universe completely. Now, let's return to the question we asked at the start. According to the second law of thermodynamics, entropy must always increase. All of our physical laws are based on this assumption. But if dark energy is not constant and instead decreases over time, the steady increase in entropy could also slow down or even reverse. Think of it this way. If dark energy weakens enough, the universe's expansion could shift into contraction. As this happens, entropy could begin to decrease. As dark energy accelerates expansion, the universe moves faster toward heat death, the point where all energy turns into useless heat. But DESI's findings suggest that if dark energy fades over time, the growth of entropy could slow down, possibly delaying the universe's death. Maybe the universe is writing its own ending with its own hands. The beauty of science is that every new discovery brings new questions. As Einstein once said, the meaning of life is not to finish the questions but to learn to live with them. See you in the next video.